Type a photorealistic frog leaping through a swamp on wooden stilts into a prompt box, and within seconds, you are watching it happen. It is tempting to assume there is a highly efficient search engine running behind the scenes, scouring the internet for separate pictures of frogs, muddy water, and wood, then stitching them together. But a composite image cannot account for the accurate reflection of water on the amphibian skin, or the perfectly calculated center of gravity required to maintain its balance in motion. The system has not retrieved a single image. It has never seen this exact swamp or this specific frog. The video you are watching was sculpted from pure mathematical static. To trace exactly how we get from a few typed words to a moving, photorealistic reality, we need to freeze this frame and step inside the computational pipeline that built it. The process begins the moment you hit enter. A language model takes your sentence and converts it into a vector, a string of numbers that captures the semantic meaning of your request. This 3D grid is latent space, a compressed map grouping related concepts. The model navigates to the intersection of frog, swamp, and stilts. The starting point is pure visual static. Through diffusion, a neural network removes noise and steps, pulling coherent structure from chaos. A mechanism called classifier-free guidance forcefully steers this loop. It compares an unguided version of the image with the text-guided version, amplifying the specific visual traits you asked for, so the emerging shapes perfectly match your prompt. Generating an image requires zero drawing. It is an act of precise subtraction. That explains how we get a single frame. But running that subtraction process on independent sequential images yields chaotic flickering. Without knowing what it drew previously, the model hallucinates wildly. Modern video models solve this by compressing the entire clip into a single block of data. This 3D cube visualizes the whole video at once, broken down into space-time patches. A transformer network analyzes all of these patches simultaneously, instead of in chronological order. This massive web of simultaneous attention enforces physical causality. By cross-referencing every patch, the system ensures that gravity, lighting, and momentum remain consistent from the first frame to the last. Once the physics and visuals are fully resolved in this compressed latent state, a decoder takes the data and translates it back into raw, high-resolution pixels. The final output operates as a fully simulated micro-reality, governed by mathematical rules of causality from the first frame to the very last. Despite the sophistication of this pipeline, it still has highly specific blind spots. In this photorealistic portrait, the hands feature fused joints and structurally impossible anatomy. This breakdown happens because hands appear in the training data in millions of overlapping configurations, waving, holding objects, resting. The AI calculates an ambiguous, averaged mathematical representation and occasionally attempts to render multiple positions at once. We see a similar limitation in this cinematic storefront sign, where the neon letters form decorative, unreadable glyphs. The AI understands the visual aesthetic of typography, but it lacks the rigid, sequential logic required for spelling. Beyond rendering artifacts, the underlying mechanics present immediate ethical complications. Mapping these vast latent spaces required scraping millions of copyrighted assets without consent, and the ability to dictate photorealistic video directly from a single text prompt makes the generation of highly deceptive media completely trivial. We have compressed the physics and concepts of reality into a statistical model. The barrier between human imagination and photorealistic execution has been collapsed down to a single text box.